Okay, friends, let's wrap up everything from the past 5 videos, and in some ways, the entire course, into this thing called the mighty Central Limit Theorem. Don't be afraid of that term, Central Limit Theorem. It all has, all those words are important. The mighty, I added myself, because I do believe this thing is super powerful. It permeates all of statistics, any inferential stat you might do or read about or consume later in life. This CLT, Central Limit Theorem, is behind it. Okay, so why do we do statistics? Well, just like always, we want to know something about a population, usually an average. But we can't unless we do a census. So the best thing we can do is take a sample of size n. Now that sample is going to have an average. We usually call it X bar. The cool thing about the sample average that you draw is that sample average, no matter what the shape of the original population's distribution is, your sample average is going to be in a bell-shaped distribution. And more importantly, the sample average normal distribution, the high point of that is going to be right on top of mu, which is the population average. I've actually seen this old notation used sometimes by the old school statisticians, X double bar. So X bar, as you know, is the sample average. The X double bar is the average of all of those sample averages. So on average, the sample averages are equal. That is an equal sign, exactly equal to mu. Now the catch, of course, is that there are some sample averages that are not exactly equal to mu. There's variation. This is why it's a bell curve and not one single straight line sitting on top of mu. So you have to control for that sample average deviation. And how do you do that? Well, sample standard deviation, as we've talked about. Now, in the inferential world, that's called the standard error. I've mentioned that a number of times in the previous videos. And as we just saw, it shrinks as your sample size gets larger. That's why the bell curves were getting narrower and taller. When I asked you in the previous video, do you see how the sample sizes 4, 9, 16, 25, and 100 were related to those multiples of 2, 3, 4, 5, and 10? Maybe you did. Maybe you didn't. That's fine if you didn't. But those numbers, those multiples, 2, 3, 4, 5, and 10, were square roots of the sample size. You may have been wondering, why is he using numbers like 4 and 9 and 16? They're so weird. It's because they're perfect squares. And I wanted to tease out this equation right here. The standard error of a given sampling distribution is actually mathematically equal to whatever the population standard deviation is divided by the square root of n. Don't memorize this formula. You don't have to. But if you take later inferential stat classes, you're going to see square roots of n in denominators all over the place. Now, why is this important to us? Well, you've been saying since week 2, the larger the sample, the smaller the margin of error. This is mathematical verification of that fact. Not only does it get smaller as a function of the square root of the sample size. And that, to me, is one of the more beautiful parts of statistics. But for you, and for users of statistics, not necessarily freaks like me that think this stuff is beautiful, the standard error, since it's on a bell curve, and it is, as we said before, the standard deviation of a bell curve, that means you can utilize all the ideas of confidence. That means that you can build margins of error around your sample. So check this out. This X bar minus 2 SE and X bar plus 2 SE on either side, you've just simply be calling those margins of error. One margin down, one margin up. And mu is in the middle there because 95% of the time, you're going to trap it between those endpoints of that interval. The standard error is simply the smallest building block of the margin. You can have as many standard errors as you need. And all that means is, as the sample gets larger and larger and larger, the precision gets better and better and better. So these ranges down here, these minus 2 SEs and plus 2 SEs, that's 95% of the data, but it's going to continue getting closer and closer and closer together, which means eventually that region, that interval, can be as narrow as you need it to be, assuming you can get a sample as large as you need it to be. Now that's a whole lot of yays if you're counting. But that's why I call it the mighty Central Limit Theorem, and I do love ending the course with it. And that, my dear friends, brings us to the end of Math 243. Yeah, so some of you might go further. You might take other stat classes, you might take research methods classes, maybe even junior or senior level statistics classes. But this is a great foundational statistics class and a great place for us to stop, because I'm sure you're sick of watching these videos by now. So I will say thank you very much. It's been a pleasure working with you all, and best of luck to you in the future. Talk soon.